Hello, everybody. So this is the network coding, for the coding for efficient network communications research group. We are on time, but maybe we can wait 1 minute, 1 more minute. This is the first afternoon session, so maybe it makes sense to wait just a little bit. The agenda is not totally full. We have 20 minutes balanced time at the end. So if we need, we can discuss just a little bit more. It's feasible this time. So let's wait a little bit before starting.
Alors, tu vas passer, tu me donnes, tu changes de place avec moi pour que je puisse avancer les... Oh, donne-moi le cliquet, donne-moi le cliquet. Je vais utiliser le cliquet. So, good afternoon, everyone. This is, again, like Vincent was saying, this is the Coding for Efficient Network Communications Research Group. If you're here for this, great. If you're not, you're going to have a great meeting anyway. And you're going to learn about something fantastic. The goals that we repeat at every meeting is that we would like to foster research in network and application layer coding to improve network performance. And I must say that if I look at the people around this room, a lot of them have been very successful at this. We want, obviously, to focus on the codes themselves and the libraries to be able to implement them. We want to look at the protocols beyond the codes, but the protocols to facilitate the use of coding in existing systems and existing applications. And we are welcoming all the time, and you're going to see some of this presented today, real-world use cases and work in progress in the field. The Node-well, which is the usual IRTF, and the same, actually we share it with our friends in the IETF. It's about anybody who has issues, and especially patents and things, they have to be disclosed. We have all of these wonderful sites and mailing lists, and the slides that we have today, and obviously we'll have a bunch of people on MeetEcho, so we'll say hello everyone on MeetEcho. I would say the interesting thing that you should know is that we've started to make a huge usage of the GitHub instead of relying on the wiki and a lot of stuff that was in the data tracker, because we feel it's easier to manage and it's easier to collaborate. It was very difficult to update the wiki when you have 2 or 3 people doing it. So you will see that if you go to the wiki by any chance, you're going to see that essentially you've been sent to the GitHub, and all the latest document and the latest comments, including the code that we've been developing over the weekend, are there. So, tu veux faire l'agenda? Okay, so the agenda is kind of very simple. After I'm done talking, we're going to talk about what we did on Saturday and Sunday. We're going to have a quick update on the satellite document that is very much ready to publish now, frankly. We're going to talk about another update of something that is also very close to be able to publish, which is the network coding on CCN and NDN. We're going to have a fairly extensive presentation from Muriel and Kerem, who are on the MITECO on basically RLNC, the random linear network code. Then we were going to hear from François Michel about the progress that was done and also some of the work that we intend to continue about adding forward error correction to QUIC. We're going to have Morten, who is in the room, talking about coding for low latency. And finally, and not, finally, but not to be forgotten, we want to talk about what's happening about the RLC, what now we call it, which is related to the Swift codec, and the standardization related to it in the transport group, and raising some of the issues. Obviously, future meetings, the hackathon, we'll have another one. We had so much fun. We want to repeat the experience. And by the way, if you have more women who would like to come to the hackathon, there was I was at the sisters' lunch right now, and we said that the problem with the hackathon, it was like you could see huge amounts of men, but there were not a lot of women. So I encourage more women, although I'm speaking to a room here where also there's not a strong number of women. And we are going, obviously, to meet in Montreal. And if anybody wants to have any hints about Montreal, it's my hometown, so send me email. And without further delay, we're going to go to the first presentation, which is, it's Nico, right? No, it's you for the hackathon. It's true. Yeah, yes.
I'm quick feedback.
Fantastic. Switch avec les clickers.
Yes. Hello. Yes. So the goal is to do a quick status of this hackathon project that we started in previous IETF 103 in Bangkok. So the hackathon is about this Swift codec. Swift stands for Sliding Window FEC codec. So as I said, this is the second hackathon. Second time we meet for this project. The goal is to design an open source reference and free codec with, as a first sub-goal, being able to do an RLC-like codec, and as a second goal, an RLNC-like codec. So for the first time, we will only focus end-to-end communications, one encoder, one decoder, and as a second goal, we will have this RLNC network coding with potentially the capability to do re-encoding within the network. So that's the goal. And of course, the final objective is to have this technology easier to test, to integrate, or to benchmark, facilitate adoption. Another goal is to challenge our generic API internet drafts. I will come back on this later on. So during the first IETF 103, I was almost alone. So this time there was a great team. As you can see, it's almost balanced in terms of gender. We had 2 women, including Marie-José and Umeima, and 3 guys. So it was great. We had a lot of fun, and we made a lot of progress. So yeah, this is exceptional. So we made a lot of progress. I mean, more specifically, that we managed not to finish the encoder, but we are not very far from the end on the encoding side. So we are capable of submitting new symbols and computing random linear combinations of new symbols and closing the session, things like that. Even if there's still some tests ongoing. We are not very far from the end at the encoding side. So the encoder is the simplest part. Next time we will have to do the decoder. In fact, we started the decoder program, but it's not yet very well advanced. So we'll have this as a goal for next IETF. We also wrote a teeny client-server demo application. That's also another way to test the codec itself. So it's great, and we have almost finished this part of the work. And we started a Python wrapper on top of this, on top of the API, to have the ability to integrate this C codec into Python applications. I won't come back on the design principle of this codec. We already discussed this in the past. So the idea that, okay, this is just the core part of the FEC codec. Many parts of it are left to the application, so the signaling, all this stuff is managed within the application. So I won't go into these technical details. Something great with this hackathon project is that it enables us to make progress also on the internet part, internet draft generic API part. So we, as we do the work, technical work, we identified a few problems. We solved some of them, so we made a few fixes in this internet draft, 4 or 5. And we also identified open points, that is to say, technical aspects that we need to figure out how to solve in the coming weeks. So all of this is documented in this GitHub document. So if you want to have a better look at a more detailed view of what you have done and what remains to be done to address those open points, then you can have a look to this document. So next step will be to continue this work. So it will be in Montreal, IETF 105. That time, I hope we'll be able to finish the encoder and to have a working decoder so that we can do interrupt tests between the encoding and decoding sites. So that's the goal. We'll see if it is reasonable, if we can achieve this, but maybe it could be possible. Also, there is a lot of cleanup, all those stuff of things to do on the side aspects of the codec. But that's the goal for next IETF. And then for the IETF 106, we'll start working on this re-encoding capability that we want to add into this project, so as to be RLNC, to have an RLNC-like solution. So at the end, we will have both support for RLC, for purely end-to-end encoding, decoding, and RLNC with the capability to have this re-encoding within the network. So that's all for this hackathon project. Just want to say something else. Marie-José sent yesterday an email asking for research group adoption of this document, the generic API document. This is something that we already discussed at previous IETF. So there was 2 positive opinions on doing that. On condition, we have this not only one codec, but the ability to test, to stress this API with 2 different codecs, which is exactly what we want to achieve. So if you have an opinion, if you agree, disagree, do not hesitate to send your opinion to the list. The fact we have this document as a research group document does not mean that we necessarily need to publish it as an informational RFC. That's a side question. We'll see that later on. It's not very usual for IETF or IRTF to have API documents, so we will see if it makes sense later on. But anyway, it's important, I think, to have both works in parallel, since there are major connections between the 2. So that's it. If you have comments, questions, is it okay? Okay, so let's continue. Yeah, Nicolas?
Hello, everyone. That's a quick update on what we have been doing in this draft since the last IETF. So the next and only slide I have is basically we had lots of, at the IETF, we presented this document in front of the DTN working group as well, to see if anyone volunteered to review it. So we had lots of comments from Lloyd Wood and lots of emails exchanged. He had lots of good points, and try to sum up here what we have done. Basically, at the beginning, we wanted to have lots of people on board on trying to speak about what was actual deployment on network coding in higher layer in the SATCOM systems. We failed to do that. So we have more focused on identifying opportunities. So we somehow had some words in the introduction that were not really accurate. Also, we had normative references which are not relevant for a research document. We had an acronym list that was not up to date, and we were not clear on whether physical layer coding were involved or not. So basically, we removed any mention to physical layer coding. So we haven't had many feedbacks since, and we believe the group is the draft, if still relevant for being published as an RFC, is ready to do so. That's what I had to say.
Questions, comments? So we had, it was great because since last IETF we had a lot of interaction. Yes, there is a GPO at the end. It will be a research group, that's for sure.
Right.
So you had many discussions with Lloyd Woods. It was great because I think it made the document progress in a good way. Yeah. So if nobody objects, maybe we can start a research group last call on this. We'll see that on the list anyway. But typically the idea is to have this 3 weeks period for research group last call. And hopefully people will comment. I will anyway. Does anybody knows that he will read and comment this document during this last call? How many people? Yes, one. Great. Okay, so at least 2 with me. That's great. That's the minimum. I hope there will be more people, but anyway, it's a good start. Yeah. So, perfect. So thank you.
Thank you.
Nothing else?
No?
Okay.
Unless you.
Thank you. C'est Kazoo. Yes. Okay. You have the floor.
Hello, I'm Kazuhisa Matsuno from NICT. So let me talk about a quick update on network coding for CCN and NDN requirements and challenges. So first, let me talk about this draft summary. The main objective is to introduce the research results related to this topic and establish the common understanding about NC4 network, CCN and NDN, and is to clarify the requirements and also to describe the research challenges. So by doing so, we hopefully we provide useful insights to network coders who try to implement network coding into CCN and NDN. So this draft now focuses on the requirements. So describes the specific solutions and or mechanism out of scope of this draft. So actual protocol proposal will be done in another draft. So regarding minor update, we addressed missing content, such as we added the backward compatibility section because there's no description about these requirements. So we describe the network coding compatibility with regular network operation with consideration for smooth migration. And also we added the content regarding security, privacy, and routing in the challenges section. So network coding operations and in-network caching are related to content poisoning and cache pollution attack. And the network coding may offer encoding vector modification by attackers. So practical solution is a real challenge to avoid them. And also, along the context of the requirements section, we added a routing challenge in how to achieve a scalable and efficient routing scheme to achieve more high performance, as well as to simplify the routing process. So today we got very good useful comment from Cedric-san from India. So and after we address the comments we get, we want to ask RG last call. Thank you.
Yes, so thank you. So what's your plan? You intend to address those comments in the coming weeks? Before next IETF anyway, but quite soon? That's the idea? Yeah, okay. So
I have one question. So last call, can I do last call in the mailing list?
We can wait for you to update your documents. This is why I asked the question. And then, in accordance with Dave and the ICNRG research group, we can organize this last call. So I don't know how exactly to proceed.
So Dave Oram with ICNRG chair hat on. I think that at this point, we have some concrete comments. They're enough to respin the draft once, and it'll be simple. My suggestion is just go ahead and do that now. And then we'll send that draft around. I'll make sure that it gets some review in the ICNRG. See if there's any further things that the ICNRG thinks and the NWCRG thinks, and with the goal of turning into a last call well before the next IETF, right? See if we can turn this around in a month or two. Does that make sense?
Yeah.
Thank you.
Thank you.
Okay, so thank you.
Hi.
Yes, hello.
Hello.
Hi, everyone. Okay. On monte vos slides là, qui ont commencé.
Parfait, bien sûr.
Thank you very much. So,
Kerim,
oui, yes.
can you put the slides on again, because there's other people on Meeteco who needs to see the slide. For now, we just see your faces.
All right. Okay. So you want me to put the slides on my camera?
No, just close your picture camera.
Okay, I can do that.
Great. Thank you.
Thank you.
Can you guys see the slides now?
Yes.
Yes, it's okay.
Super.
You can. You have the floor.
All right. So on the first slide, this is just really giving an update on what happened to draft HIDA NWCRG RLNC00. So remember just a little history here. This was submitted in February 2018. This document contained a large background section and it was focused on symbol representation, still is. So we submitted 2 updates to that document. So we separated the background into a separate background document, which is informational, still pretty much oriented towards symbol representation, so it's not completely an RLNC background document. And then the second one is dedicated, we updated the second one, they have 01, and it's dedicated to symbol representation. This is collaborative work between Steiner of Codon and Inmarsat, although we're speaking in the name of all the authors here, so Muriel and I. So moving to the agenda slide. So as I mentioned, we split the document into background informational, and we kept the symbol representation itself in the updates, RNC01. I'll just give a quick view of the scope. We have new definitions that are in these documents, a couple. We have one or two important new sections, and then I'll cover what we look towards doing for the next version, future modifications, mostly from comments from the email list. And of course, if you guys have comments in this meeting, we'll add them up and respond to them. So going to slide 3. Just I'll give an overview of the current changes that we have here. So in the first document, the informational, as I said, it's a general background informational. It's supposed to be on RLNC. That's the goal. It's a document in development. Still now it's focusing on really the background required to read the symbol representation. So an important section was added, which is really viewing symbol representation as an important standardization target. We actually argue for that in this document. And then in the second document, which is the symbol representation specification itself, I just added a couple of definitions, and we improved the figures. Most of these comments come from Vince, so thank you very much, Vincent. And that's it. So let's go to slide 4. So on the definition of symbol representation, really we spelled out the definition. You see there's a slight difference, but it's basically the same. We are talking about the symbol carrying data unit. This is what you're going to have on the wire. It's not, of course, what's going to be used in the encoder or the decoder. That's different. So if you guys have any, comment on this definition, this is a good time to say. So a disclaimer here, most of the points I'm going to say after this with Muriel are really touching upon some of the comments on the background section, and also I'm going to cover what we added in the background section, the section about symbol representation. So you see here the figure is really the fundamental concept that you have in the experimental draft, which is the second version, RLNC01. So in addition to changing adding this definition, we really just changed the format to 32 bits. That's all there is to it. If you have comments on that draft, feel free to send it on the list, and we'll take care of those as they come in. All right, so I'm on slide 5 now. So the major argument for standardizing symbol representation, according to us, is that, there is a lot of flexibility in RLNC. And so we really need the standard. I mean, that's for sure. Once we have it, it's going to be highly reusable. And so the point is, of course, that RLNC is very dynamic. The structure is dynamic. The symbol set is very reconfigurable. So examples of reconfigurability are given. We mentioned coefficient location. You can cluster the locations at the front, which is done actually in the symbol representation. You can put a seed, which is something completely different. And you can also do an indexed representation where if you have just a few coefficients, you can put them, really on juxtaposed one next to the other, each one of them having an index, indicating which symbol they refer to, basically. So there's a lot of flexibility. The reason for this flexibility is that symbols and RLNC payload can be, you can operate on it. You can use linear operations on it without actually necessarily knowing the location of the coefficients. So once you put them there, you can. It's the same operations that are done for the payload and for the coefficients themselves, which is really a unique aspect of this code. So that adds flexibility. That was point one. So point two is the, of course, the number of coefficients is quite dynamic. Also the number of symbols. So you can have dense codes, you can have sparse codes, and actually the sparsity can be even dynamic itself. The third point of flexibility is the symbol size, clearly. You can have larger symbols or smaller symbols. I will define actually some of these concepts later because we've had questions about this. But if you're expecting in your network to have anything like fragmentation, padding, or even encapsulation, which is standard procedure everywhere, then this is very useful. So this flexibility is useful. And then finally, the field, even the field, which is you can think of as something fixed in most applications, it can be flexible. There are interesting use cases where you can make the field flexible. You can control the complexity of the coding. You can actually deal with different device capabilities. Some of them can deal with higher fields and others with just smaller fields. So you can have flexible fields. And one of the interesting things about RLNC is that the same operations can hold for different fields. That's another discussion. So this is what I have on this slide. On slide 6, I was going to just tackle one example. So as we said, network operations will be affected by symbol representation. So an example is fragmentation, and it's very simple. Either you know where your coefficients are or you don't. And if you know them, then you can separate the coefficients and do the fragmentation. That's what you see in the figure A, code-aware fragmentation. You can actually run recoding and modify the code on the different fragments, and then you can do the decoding. If the coefficients are unknown, so this can happen also. I've received comments on that on the list and replied to some of them. So suppose you have a file which was pre-coded at a different layer, so you know it's coded, but you don't know where the coefficients are. Then you basically have to, if you need to do coding on the different fragments, you have to add new coefficients, and that's what we call by adding a new layer. Basically, you don't use the same coefficients, you're adding another layer of RLNC that you need to deal with, of course, at the decoder. Okay. So, of course, if there are questions here, we're happy to respond. So I'm moving to slide 7. So here's slide 7. It's still, arguing for the standardization symbol representation. So the point here is, there was a figure similar to this in Janos's presentation in London. Janos mentioned, and it's true that, of course, symbol representation can be reused by multiple protocols. Symbol representation also affects the architecture, the layer architecture. It affects the coding topology that you can use. All right, we've received some questions on this too. So when I say architecture, I mean, of course, the layered architecture, where you put the coding. You can be using the coding for routing. You can just do the encapsulation as mentioned earlier. These aspects are affected by where the coefficients are, for example, and other aspects. So on the topology side, we are talking about the logical coding topology, and a good example is whether you need to do recoding or not. If you need to do recoding, then the coefficients need to be apparent. If they're not explicit, then you can't really do recoding. You're left with end-to-end, basically. If you can do the recoding, then you can do a lot more, specifically mesh and cooperative operation, right? And of course, the protocol, as we mentioned, generation versus sliding window, that's pretty obvious. All right, so now I'm moving to the next section, which is overview of suggested changes. I'm on slide 8. So on this, we have received comments from Dave and Salvatore mainly. Salvatore Signore, thanks. And also Dave Oran, thank you very much. Multiple comments. And on the background draft, we're looking at substantial changes. So there'll be a bunch of definitions that we'll add. There's a lot of networking terminology that needs clarification or correction. We agree to that. There is, Dave mentioned trade-offs related to coding parameters. We talk about that a little bit, and of course, the security section. We'll discuss what we put really in the security section. On the RLNC draft, so the second version of the symbol representation, it's really just maybe some clarification of definitions that are required there. So again, if you have more comments, send them to the list. So I'm going to slide 9. So just an overview of the kind of definitions we're going to be looking into. So first of all, I mean, before the definitions, networking terminology. So yes, there is a little bit of wishy-washy use of the word connection. Marie-José mentioned also in an email just earlier, link versus channel and losses versus errors. So most of this stuff comes from really, I mean, different backgrounds of people, people working in communication theory, maybe information theory versus networking, different terminology. So I go back, I mean, I'm going to say from, from the get-go that yes, we're going to look at the taxonomy draft, RFC 8406, and maybe connect our document with that a little bit more, refer to that. Some of the definitions, some of the terms that I think we're going to be using are, we're going to say field elements rather than symbols is not really, I mean, symbols is used in communication theory to mean, it's related to modulation. So it really means field elements here. We're going to use field elements. What we mean by symbol here is more the networking coding implementation term, which is really the coding data unit. It's an array of field elements. Raw data, I mean, Janos mentioned, this is a good term, I think, raw data. It means anything like uncoded or systematic or raw symbols, input symbols, application data, all of that has been used. We'll check the taxonomy, but we'll probably be using raw data. So again, I mentioned representation is what goes on the wire. It's different from what the encoder and decoder have. So this is not necessarily the data structures in the nodes. It's really what's on the wire. We agree on that. So coding layer is interesting. So I mentioned in the example of the fragmentation, and so you basically by adding coefficients, and when you do a new operation of coding on top of already coded data, if you don't know the coefficient, then you need to add your coefficient. So it's as if you're doing the coding on basically new uncoded data. It doesn't make a difference. So that's what I mean by adding a new coding layer, and I mentioned that earlier. There is two other aspects we'll be mentioning in the next slides. Coding vector, which comes back to a point from Salvatore, and also the concept of hidden coefficients, which is related really to the security. So that's slide 9. So slide 10, on the coding vector. So I'm just going into a little bit of detail. So yes, I mean, I already explained all of this. The raw vector is the coding vector. The coding vector is really what is used as in the encoder and the decoder. So if you see the figure on the right, this is the basic coding operation, where you have the symbols lined in a matrix, which is basically your generation or your window. And then you have a coding vector multiplying that to get a coded symbol. And each one of these symbols has field elements. So what we mean by coding vector is really what you have there on the left. It's the full vector, including as many zeros as needed if you have sparse coding. It's definitely not what you'll be sending on the wire. It doesn't make sense if it's a sparse code. There are different representations that you can be using. And that's actually an important aspect of the second draft that you can look at. So I think I mentioned all of that. Yes. Yeah, the two main aspects really for the representations, you need to have the value of the coefficient, but you also need to have the mapping between each coefficient and the symbol that's related to. So any way you devise of doing that is a representation. Okay? And yes, Muriel is pointing to just the fact that, I mean, there are examples of representations. So either you send the raw vector, which is the whole thing, if you're using dense coding. If it's sparser code, then you can just go with the coefficient values plus symbol indices. This is used, for example, for SS09, one of the references we give in the document. Yes, you can send the seed, which is also specified in the symbol representation draft. So that is on the coding vector side. On the protocol trade-offs, so that's an important point. I have to say we tried to avoid this a little bit because we didn't want to go into protocol aspects, but they are related to many of the parameters that are explained. So we agree. I think we're going to do some, at least the fundamental trade-offs we're going to mention. So basically the field size, having a larger field size, meaning if you have a larger field size, then you have higher diversity. It's less likely to have dependence, and it's higher complexity. That's a basic trade-off. Also, if you have a smaller field size, you'll need to send probably more redundancy because of the possible linear dependence. So, working on that, I think that's an important trade-off, which is fundamental. The symbol size in between and the generation size is also pretty clear. So the larger the generation, the higher the latency. You need to assemble your symbols, your coded symbols, before you can actually deliver to the application layer or to the next layer. So that's important. So there is a latency throughput trade-off there that we can explain. There's extensive literature about this too. And of course, the granularity of your redundancy, of course, the larger the generation, the larger the window, the more you can be specific with your feedback. So sorry, I mean with your redundancy. So one packet basically is if you lose, for example, if you can have better granularity, finer granularity is the word, and we will explain that. We'll explain that in the document. So I'm looking at the time, and frankly, I need to move forward. So other optional trade-offs we might touch, but we don't think really are necessary at this point is, of course, whether you do a block code or sliding window really is a design issue for the application. We might brush on that, but we're not sure on the fence on this. Systematic versus full coding, sparse and dense coding, what it means, and also using feedback versus no feedback. These are issues that really go to the application themselves. So we're thinking about that. Okay, so slide 12 is on security. Well, I think I'll let Muriel say a few words on that.
Yes, and thanks to Dave for pointing out that this would be an interesting topic. So there's a huge amount of work that's been done by a group, but also by some others on security. And really what we're concentrating in here is, again, just how this connects to the representation issue. So this is not a comprehensive view of security. But the initial assumption that we have here is that we're operating for the security aspects within the coding layer. So we're really just focusing on the coding operation and the aspects that are coding specific. So network coding operates, of course, by allowing a mixing of data. And the natural question is, what are the security consequences? One, are there extra vulnerabilities that open up? But two, what are the extra possibilities also that this provides? So, one of the things that this allows, of course, is data hiding. The encoded data in the absence of information about how to decode it is, of course, actually very well protected. It is related to, sort of Shore style of post-quantum security, actually. So it has very strong data hiding, and we can do things such as, basically trusted storage over untrusted networks. The thing that people, of course, sometimes worry about because of the fact that you have the mixtures is this issue of pollution attacks, sometimes called Byzantine attacks, because it could be insider attacks by nodes inside the network, say in a peer-to-peer system, or when you're recoding if one of the intermediate routers were compromised. So then there's a lot of possibilities around detection and correction. Some of them are related to the representation, some of them are not. It would actually take a lot of work to go into all of those details. So we're still, as Kevin pointed out, sort of trying to figure out how to go into this, because it could become an entire tutorial, and there is work on that. The other aspect, of course, is the aspect of verification. Just I want to say for the Byzantine attacks is, of course, you can do both detection of Byzantine attacks, either end-to-end or at intermediate nodes, even at nodes that don't have enough degrees of freedom to decode. You can also do correction by combining it with an error-correcting code. The last aspect, which is that of verification, is something where that touches upon homomorphic encryption. I just want to point out that we don't necessarily need sort of the more sophisticated elliptic curve style verification with homomorphic encryption, but the network coding aspect does marry well with homomorphism. Basically, what you need is homomorphism after the linear operations of the coding, and actually fairly simple discrete log systems a la Diffie-Hellman are perfectly compatible with that. So again, we're trying to figure out, how much you can want to give. That's a very rich area, but we agree it's an interesting one. So back to Katie.
Perfect. Yes, so there will probably be something in the section which is more than what you see here, but I mean, it will not. I mean, we're still discussing how deep we're going into that. So as Miran said, one last point on slide 13 is yes. Some people on the list mentioned some added references. Definitely the terminology that needs to be looked at, the RFC 8406 taxonomy, maybe a couple of more references about related to symbol representation. There's also a question on encoder rank. We saw that from Salvatore. So all of these we'll respond to in due course, definitely. And of course, if you have last slide, if you have any comments, questions, or suggestions, do not hesitate to send them on the list, or just come up to the microphone and tell us now. Thanks.
Okay, thank you for this detailed presentation. Are there comments or questions in the room or on Mixteco? I have questions. Karim, you mentioned, I think, on slide 5.
Mm-hmm.
Yes. On slide 5, you mentioned that there is this dynamic number of coefficients and symbols. Yes, but if I'm looking at the header, I see a 4-bit field, meaning that you cannot exceed 15, 16, depending on how you count.
Okay.
Is that flexible? It really depends on what you want to achieve with which field size, things like that. 15 is not that much.
Yeah, I agree with that. So there are two actually. There are two different sizes you'll see. I think I'm not sure both of them are just 15, but yeah, I mean, I'll look into that. But it's I thought there was a large field and a small field for that particular number, but yeah, so I'll check that to make sure. But I mean, we are saying, I mean, the point is maybe this symbol representation doesn't show that aspect, but it is an aspect that needs to be addressed, right? So
yeah, just to add to that also, if you're using it as a seed, then actually what you have is a very different dynamic there in terms of the number of choices.
Sure.
Mm-hmm.
Yep. Which leads to another comment. It's great to have this specification of full specification of the headers, but if we want to go into that direction, then we should make attention not to close doors, and by being too specific on this aspect. So it's a difficult exercise to keep the high flexibility of RLNC that you mentioned. I fully agree. And at the same time, specifying something which is very detailed in terms of header format.
Yeah.
That's a difficult exercise. We need to discuss this on the list more in detail, because this is a key aspect of this type of work.
No problem there. But again, I mean, this is one symbol representation. So what I mentioned, remember what I said in Montreal, is that we might end up with a couple, 3 or 4 different symbol representations, each geared to a class of applications. So I mean, it doesn't have to be all full flexibility, and it doesn't have to be also too rigid. So, and that, yeah, definitely a discussion for the list. We agree.
And just to echo that, you know, in our own work on network coding, we have had different representations in different implementations that we have done. Again, sort of depending a bit on the application.
Correct.
Yes, and is the goal to have those different representation specified in this document, or is it open to also documents? How do you see the way this document could evolve in terms of representations, as you mentioned?
I think.
So do you intend to add more than one?
Sorry, go ahead.
Do you intend to add more representation in this document?
So not necessarily. I mean, I think representations can be added by in different documents. I think it's not a bad idea to have maybe a certain number of documents, each addressing maybe a class of applications. This is the first effort. I mean, it can go either way, frankly, so we can discuss it. But as far as I see it now, clarifying this one and putting it down, I think is useful. And then we can take it from there.
Yeah, I echo Kevin. Basically, the idea is to have a useful document here that's concrete in terms of the representations. Not to close doors to other representations, but to provide a serviceable one.
Yeah, I agree. Since you're mentioning the possibility to have a seed, it means you have a PRNG associated to this. Do you also intend to provide a list or suggestions in terms of PRNG? I'm asking the question because the last item in the agenda today is about our experience in terms of TNMT32. I will have to come back on this, but what's your goal?
Okay, so yeah, so that's a good question. We had it also on the list. So our initial thought was to have that part of the protocol specification and negotiation. I think that's a natural place for it. We are really, really specific to the symbol representation here. So yeah, that can be, I think that can remain outside. Yeah, I mean, we're open to discussion here. If you think it really has to be part of it, I don't see now why it should be part of it, that's all.
Yeah, I think, again, we're just trying to give a useful symbol representation which is serviceable. And just it's a narrow but concrete and we hope useful contribution.
Okay. I see you have extra slides. We have 5 minutes left. If you want to...
no, that's okay. I won't bore you. I won't bore you.
It's up to you.
No, that's fine. That's fine.
So those are for in case we had questions, but it sounds like it's fine. Please send your comments on the list. I mean, that's really the best place to start discussion.
Yes, and thanks Vincent, Salvatore, and David for the comments.
Yes.
You're welcome. Is there another comment or question in the room or elsewhere? Miteko, no? We are done? Okay, so let's continue with the next presentation from François. Thank you, Karim. and loyal.
Thank you.
So, hello everyone. So first, please forgive me for my speaking and hearing abilities, because I've got a cold that I just can't get rid of, but okay. So I'll here present our work on implementing a forward erasure correction extension to the Nwcrg protocol. So first, a quick reminder about the Nwcrg protocol. So this is a transport protocol providing a reliable and secure transport of data. And it also provides stream multiplexing in order to avoid problems such as head-of-line blocking. So FEC was part of the early Nwcrg versions, but it has been dropped due to bad experimental results from the early designs. So now the reliable transport is only ensured through the retransmission of lost data. And now we will consider to add the extension again to recover from losses without the need for a retransmission. So how does a Nwcrg packet look like? It's just composed of a header and a payload. The payload is itself a sequence of frames. So let's take an example. Here we have 3 frames in the Nwcrg payload. The first one is an ACK frame, which acknowledges the received packets. And the 2 others are what we call stream frames. They carry user data for 2 different streams. Here, the stream X and the stream Y. So there is already a design for a FEC extension proposed by this research group. And we started an implementation work of a FEC extension for the Nwcrg protocol in parallel to this draft. So we started when the current version was not released. So we have quite a different design, and we will discuss the differences here. So we have 2 implementations, one using the Nwcrg Go implementation, which is based on the Google Nwcrg design, and a second implementation working on Pico Nwcrg, which is based on the IETF Nwcrg design, draft 14. So I will show some frame formats, but we do not intend to propose it as a standard, so we just want to discuss the ideas, not the details of these frame formats. So let's first take a look at what the current draft is proposing. So we want to define what are the source symbols, which are the data unit that we want to protect. And the draft proposes to chunk a stream into blocks of fixed size. The size is called E. And so we will chop a stream into several fixed size chunks, and we will consider these equal sizes chunks as our source symbols. So here on the figure, we can see that we have 10 source symbols, and the last one is incomplete because the stream is finished before the end of this chunk. So there are some advantages of proceeding like this. First, we don't need any signaling to identify the source symbols, because the server and the client only have to agree on the size of the chunks, and then they don't need to advertise which part of a stream is a source symbol, because it's implicit. Another advantage is that there is no control overhead, because we only protect the user data. We don't protect any frame header or thing like that. We focus on user data, so that's another advantage. On our side, we started to implement some FEC extension with a different approach. We decided to consider a packet payload as a source symbol instead of string chunks. So here you can see on the image that the packet header is not really part of the source symbol. Only the sequence of frames is the source symbol. So this approach also has some advantages. First, we don't need to agree on a symbol size, because if 2 packet payloads have different sizes, we can consider that one of the 2 source symbols will be padded to match the size of the other. And as Nwcrg naturally handle padding, this additional padding will be understood as padding frames. And having not having to agree on a symbol size also helps us to solve the silent period problem, which was a problem that was pointed by the authors of the draft. If you look at the figure, you can see that the last symbol is not complete, so we are unable to protect it. So if this last symbol is lost, we cannot recover it because we cannot add padding in stream frames, because it would consist in adding data in the user data. Another advantage is that we can protect more than just the stream data. So, for example, we can protect the flow control frames, and we can also protect some other frames like the datagram frames that were discussed yesterday that will provide a message mode for the quick users. We can also protect any of the frames that are not currently not part of the design, because as we protect a quick payload, we are agnostic of what it contains. So this approach, this packet-based approach, still has some inconvenience. First, we need explicit signaling to identify the source symbols, because it is not implicit anymore. So for that, we propose to add a new frame that will identify that this quick payload is considered as a source symbol. We call it the source fake payload ID frame, and it just contains one field, which is an opaque field, and this field will be populated by the fake scheme, and it will identify the source symbol in the in the coding window. Another disadvantage of this packet-based approach is that we have an increased overhead, because now, as we are protecting a sequence of frames, we will also protect their header, and so we are not only protecting the user data anymore. And as we have an increased overhead, we will more likely be in the case where a source symbol will have a full packet size, and so the repair symbol might not completely fit into one packet. So in our implementation, we restrict a little bit the size of a source symbol to be able to have a repair symbol that fits a whole into one packet. So now, so here we talked about the source symbols. Now let's talk about how we send the repair symbols. So here we have an approach that is similar to the approach described in the current coding for quick specification. So we add a new frame which will basically contain a repair symbol. So I won't dig into the details of this frame, but what you have to keep in mind is that it also contains an opaque field which is called the repair fake payload ID, and this field will also be populated by the fake scheme, and it will identify the repair symbol so that the receiver can easily proceed to decoding. Then we had to think about what to do when we recover a packet. Because in a transport protocol, if we recover a packet, we can do three different things. First, we can hack this recovered packet. So it will make the sender think that this packet has been successfully received, and then it will not retransmit the lost data, which is fine, but it won't adapt its congestion window. So if this loss was due to congestion, the congestion window won't be adapted. The other action that we can take is to just not hack the lost packet. In doing that, we'll make the sender think that this packet was lost, so it will adapt its congestion window. However, the problem is that it will retransmit the lost data even if they have been successfully received. So we propose a third way to react, and this consists in explicitly advertising the sender that we recovered packets. So we send a new kind of frame, which is called the recovered frame, and it announces the range of packets that have been successfully recovered. In that way, the server can know that a packet has been lost and then recovered, so it can adjust its congestion window, but it can avoid to retransmit the recovered data. So the format of this frame is currently very identical to the format of an hack frame. Just instead of announcing which packet has been acknowledged, it announces which packet has been recovered. So now let's take a look at some experimental results that we have performed with our implementations. So we are doing a simple request. Oh, yeah, you have a question.
Excuse me, Nicolas Kuhn, before you go to the results, have you considered sending an ECN signal?
Yeah, so basically the recovered frame is really close to sending an ECN signal. The idea is that as we can say to the sender that the packet has been recovered, it can also maybe adapt its code rate accordingly. So we have a little bit more information than sending ECN information.
I agree that you have more information. It's just maybe complex to add new frames, but you may use an actual existing vector to, because if your objective is just to have an reduction of the congestion window, that could be a way to do it.
Yeah, so yeah, I agree. So maybe we can discuss about adding a new frame or not. Yes, so thank you. So let's take a look at some results. So first, the experiments have been done with emulation using Mininet, and we are focusing on in-flight communication use case. So it's a case where there is a high delay and a high loss rate. So we used a seeded loss generator in order to compare more fairly the different solutions. So here we have a graph showing the download completion time ratio between Quick using FEC and regular Quick. So basically, if our results are smaller than 1, that means that than Quick with FEC, the transfer using FEC was shorter. And if we are greater than 1, that means that the transfer using regular Quick was shorter than using FEC. And so if we look at the small request response, we can see that for small sizes, FEC has a good advantage because if we lose a packet, the receiver will have to wait additional time after the end of the stream to receive the retransmission of the lost data. Using FEC, we can recover this lost data before the wait for a retransmission. If we take a look at the bigger, the larger request responses, like this 1 megabyte file download, we can see that adding redundancy will need some more time to transmit this additional overhead, and so it will have a negative impact on the download completion time. And so recovering from the losses, the tail losses, only adds a small gain compared to the additional overhead that we had to add to send the redundancy. So for large request responses, there is an interest in disabling FEC. So with these results in mind, we decided to perform other experiments with our PyCoQuick implementation, and we decided to only protect the end of the stream, not the whole stream. And so the results are quite similar. The difference is that, so for the small request responses, the results are quite the same. For the 1 megabyte download, we can see that the negative impact of FEC has been highly reduced because we don't send redundancy during the download, so we don't have this additional overhead, and we can still recover from these tail losses. However, we still have a small overhead because we need some signaling. We need to send these different frames, the source symbol frames and the repair frames. So it has still a small overhead, but it has been largely reduced by only protecting the end of the stream. Then we wanted to check the interest of sending this recovered frame on the congestion control point of view. So we performed experiments when two quick flows are competing. So we have one quick flow which is in background, so we call it the background traffic. And we have 3 candidates for the background traffic: a regular quick download, a quick FEC download, sending recovered frames, and a quick FEC download acknowledging the recovered frames, the recovered packets. And we studied the download completion time of a foreground regular quick traffic. So we'll see how it competes with quick FEC, sending or not the recovered frames. We don't apply medium losses on this use case, so the only losses that will apply will be congestion induced. So here on this graph, we show the download completion time of the foreground traffic for these three cases. So we can see that in the case where the background traffic is quick fake sending recovered frame, so it's the with RF box plot. The download completion time of the foreground traffic is very similar to the download completion time of when it competes with a regular quick download. When it competes with quick fake, only acknowledging the recovered packets, we can see that the foreground traffic takes a lot more time to complete. And it's just because the congestion implied losses will be hindered by the acknowledgement of these recovered packets. But we may need more experimental results to confirm the interest of the recovered frame because it's only one case study, so we might need to perform more experiments to confirm this tendency. So to conclude, we can see that fake also has an interest in the small request response use case, like some API calls, etc., especially in high delay and high loss configurations. We also see advantages in both approaches, the stream chunk-based approach and the packet-based approach, but the experiments that we did only consider the packet-based approach. So it might be interesting if somebody could compare these two approaches. However, the packet-based approach is the only one that allows to protect other frames than stream frames, like the new datagram frame. And we also saw that recovering the packet must be done carefully in a transport protocol, because if we send the wrong signal, it could lead to unfair behavior. Finally, we would also like to experiment with real setups and some real-time use cases in order to see some other advantages of fake in Quick. So that's all for me. So if you have some questions, I'll be happy to answer if I hear them.
Thank you. Yes, questions in the room?
Morten Petersen, nice presentation. I had a question on the, I'm not an expert on Quick at all, but how does the, how do you know, so basically what I saw was that when you're sending large chunks, it's better to basically only protect or large files, it's better to protect only the end, to sort of avoid this problem with the losses at the tail. Does a Quick implementation know the size of the file it's sending, or is that something that you implemented in order to get that information to the implementation?
So when we send stream data, basically a stream frame contains one bit, which is called the fin bit, which says if this frame contains the end of the stream. So basically when we see that we sent the end of the stream, we decide to send a redundancy. And we also did it for when we are what we call application limited. So if we have no stream that have to send data at all, so all streams are blocked basically by the application, then we also flush this, the redundancy.
And how would that work if you have something like, again, like if you're pipelining data, like in HTTP, typically you put more than, just a single file on the same connection because you don't want to have. So would that mean that it's only at the end of basically when you close the socket, you would protect that last piece of data? Or
so there are two ways to proceed when we want to send multiple files with HTTP. Either you use several streams, one stream per file, and in that way you know when you send the end of the stream. Otherwise, you can still do what we did in our implementation. If we don't have any more data to send, so if you are application limited, we send some additional redundancy. But if you are pipelining, like concatenating many files one after the other in only one stream, we won't be able to detect the end of a file. Yeah, so
okay. Do you know what they are planning to do if both modes are sort of gonna be?
So it depends on the HTTP to mapping with Quick, but I think that the recommendation would be to send one file by stream, or only correlated file in the same stream and uncorrelated files in separate stream.
Okay.
And so yeah, the idea is to use as many streams as you need.
Yeah. So and my second question is, where do you see an advantage in here? It's basically integrating the effect into the transport, right? But they are now doing this new datagram extension, which would essentially allow an implementation to put the FEC, on top, using the datagram, getting the encryption and the congestion control. But do you think which path do you see as the best one, or should both be considered, or what's your opinion on that?
So I would say that it depends. If your application has really strong needs and depends strongly on the shape of your traffic, maybe it's better to let the application handle the forward error correction itself. But providing the FEC on the transport level allows simple application to protect their traffic without too much implementation effort. So basically, that I think there are use cases for both approaches. But it's very good remark, because that's also what we think.
Yeah. Okay. Thank you.
Thank you.
Yes, questions in the room?
Hi, CJ from Hughes. Nice talk. I've got a very simple question. What is the round trip time for this experiment?
So we perform many experiments with many different round trip times. So as we consider the in-flight communication use case, we have a large round trip times which will span between 100 milliseconds until 700 milliseconds, which is really huge. And we perform many experiments with many different round trip times.
So between, I know 700 milliseconds, what is the lowest one?
100.
100 to
Yes.
700 milliseconds,
Yeah.
and you have many different.
Yes, so basically this is the aggregation of all the results. So we follow a methodology which is called experimental design, which consists in exploring many different values for the parameters, like the RTT, the loss rates, loss patterns, etc.
Do you have a separate result for different RTT in the paper, or no?
Sorry, can you repeat?
Do you have a separate performance result for different types, different RTT, round trip time?
So we have it in our data, but in our paper we don't show it in the graphs. But basically, if the RTT is very large, the tail losses will have a high impact.
So
If
that's the point. So I
Yes.
mean, for the geo-satellite case, if you have you have a very big difference in performance.
Yes, that's
That's
indeed.
I mean, okay. Thank you.
Yeah, thank you.
Name, please. CJ from Hughes.
Oh, okay. It's Nicolas Kuhn again. I have a question. What is, I may have missed it, and I'm sorry if I missed it. What is the stacks you have been implementing this on?
Sorry, I didn't hear.
On what quick code have you been implementing that?
So we have two implementations. One is Quick Go, and the other is Pico Quick,
Okay.
relying on Draft 14.
Okay. Thank you.
Thank you. Other questions? No, I have questions. Comments. Yeah, but I wanted to know if there are remaining questions in the room, or I need to go first. So thank you very much for this very interesting and complementary approach for addressing this problem of adding FEC to Quick. As you said, there are different design goals and different properties that results from those design goals. And at this level, it's very interesting because we don't really know what is the best approach, or is there a single best approach? It's still totally open. So we already discussed this with François, of course, and our conclusion for the moment was to, as he said, was to experiment and go into address both types of solutions and see at the end in the future IETF meetings, for instance, see what seems to be the most interesting one, or maybe we make it both of them, but we'll add some more complexity. So I'm not sure of that. But anyway, let's continue this experimental work. And let's see afterwards what seems to be the most appropriate solution before going to Quick working group in the future. So that's very interesting, and we will make those two internet drafts. Coding for Quick and ILC for Quick. I don't remember what name gave it, but anyway, we will include support from this approach, or this packet-based approach in both documents, and in order to be more, to go into those technical details that are very interesting, and assessing the consequences, the key benefits and cons for each type of approach. So thank you very much, François, for this detailed presentation of all your ideas.
Thank you.
Hi, comment from Dave Oran. I've made this before. I'll make it again just for the record. I would discourage the group from baking this until Quick decides how it's going to do multipath.
Sorry, I didn't.
I said I would discourage us from baking this too much and locking it in until the Quick working group figures out how it's going to do multipath, because there's a strong coupling between how you might want to do this and how multipath works.
Yeah, sure.
Okay.
And there is also activities on multipath Quick in the University of Louvain. So I think you are in good position to have a clear idea of how to do that, how both techniques can complement one another or not. Yes.
Spencer Dawkins. I want to strongly agree with everything that Dave Ferran just said, with the possible exception that the Quick Working Group is not actually working on multipath as a working group right now, even though it's a chartered activity. And it might be that you all would discover things doing research that they would find useful in the working group as far as being able to move things forward. I mean, you know, IETF research groups don't tell IETF working groups what to do, but if you knew something smart that they don't know, they might find that interesting.
I agree. Are we done with this topic? Yes?
Any questions on Teco?
Okay, seems to be okay. Thank you very much, François. So, next talk is from Morten. Yes, thank you.
Okay, so my name is Morten Petersen, and I hope this is not too much sort of preaching to the converted, but I would like to motivate a little bit using coding for low latency and reliability, and basically try to make the case for why, if we do not consider coding for this, then we are missing some important performance opportunities. So basically, low latency and reliability is a requirement driven by the application that is running over over the transport that we're using, and different applications, of course, have different requirements. And what we are seeing now, so some of these applications are old, right? We all know video conferencing, and they have relatively relaxed requirements to latency and reliability. But a lot of newer applications are appearing, like AR, VR, telesurgery with haptic feedback, cooperative driving, and these types of applications have much more strict requirements on reliability and latency. And if we're going to address those requirements, we need to, think about our different options for how we are implementing reliability and achieving low latency in our applications. So basically, before we go into the techniques, there's some fundamental properties about latency that's really important to understand. And basically, if you look at the latency between two given points, there's a physical limitation to how low we can get it, right? So if I have two cities in the US, Boston and Stanford, the distance between them is approximately 4,000 kilometers. And that means that if I do the calculation of speed of light through a fiber, I'm going to get something like 21 milliseconds of latency one way, and that's not going to change until somebody finds a way to improve speed of light. So basically, yeah.
Just a data point, the worst case latency, if there's been a fiber cut, is actually 190 milliseconds.
Okay, thank you.
It's way worse than you think.
It always is. So there's also some references that are not showing here on the slides, but you can, if you find the slides later, you can go in and read a little bit more about if you want to sort of fully understand this. But basically what it's telling us is that the link latency without the protocol has a lower bound, right? So if we are going to sort of put our applications on these links, then we have to take that into account. So there's another, maybe, I don't know if you can scroll down a little bit. I think my slides are. Yes. Okay, so there's another interesting thing, which is taken from a famous rant by Stuart Cheshire, who says it's the latency stupid. And basically what he's saying is, once you have bad latency, you're stuck with it, referring to this fact that, speed of light is not going to easy to change. But there's another thing, and actually that's, where the coding becomes interesting, is that making more bandwidth is easy, right? So you can always dig another fiber, or you can, buy another DSL line. So we can always make more, bandwidth, but we are not going to be able to improve our latency. So that's an important point when we think about adding coding as a solution to this. So if sort of to briefly state the problem, right, is if you have two devices that need to communicate with low latency, how can you achieve it, right? And what we are doing today, almost everywhere, if you go also to the different talks here at the IETF, it's ARQ, right? And what are you doing with ARQ? You're basically trading latency for reliability in order to minimize bandwidth, right? You're waiting to figure out which packets were lost, and then you're retransmitting only the lost packets, which gives you optimal bandwidth usage, but you're paying with latency because you're waiting to figure out which of the data was actually lost. And that can be really problematic for latency sensitive applications. And then we have another trade-off which we are advocating, right, is that you use coding for the reliability, because what you can do there is you can trade bandwidth for reliability without hurting your latency. So in theory, you can do something that is, even bandwidth optimal with coding, but typically in practice, right, we have to, anticipate the communication link or predict some amount of losses, right? And we put, enough coded data onto the wire that the receiver will be able to decode the content without any retransmissions. And thereby, we're only having this one-way latency cost added. So we have a few sort of to illustrate this point. We have a few sort of visualizations. You can go in and check where you can play around. It's basically small simulations that are running in your browser. You can go in and play around with them and try to see, what is the difference, the latency difference between an ARQ-based system and a system that uses a code, and you can try out with some different parameters and basically get a feel for the cost of the two different approaches. Coding, of course, isn't the only answer, right? There's lots of other techniques like edge computing, moving data closer to the people, having in-path retransmissions. You can do other things, but definitely it needs to be part of the toolbox that people have when they are doing these kinds of things. Also, if you want to see a real-life use case, this is a demonstration you can find on YouTube where basically there's a very latency-sensitive application. So what it's doing is today more and more services are coming which are basically like Netflix for gaming. So the game is actually running on a server in a data center, and you're streaming the video of the game to people. And they are then, playing the game, and they have to send back control input to the server that then updates the state of the game. And basically, you can play new video games on your smartphone or something else as long as it has a video decoder, right? These types of applications are extremely latency sensitive. And what we did here was that we basically tested those applications under different sort of network conditions, and then with and without coding, and basically demonstrated the user experience improvement for such applications with coding compared to just using the standard reliability mechanisms of the game streaming application. So when you walk around and if you look at the different drafts that there's actually, because of 5G and all this stuff that is happening there, people are, sort of becoming aware that low latency is going to be a fundamental requirement for many of the applications that are proposed for 5G. And also at the IETF, people are thinking about latency, right? But nobody mentions coding as a potential sort of solution for this, and that's a little bit problematic. And of course, we are here, but it seems that we are not very good at communicating to the rest these kind of things. So maybe this is something that could be, a draft for the working group, something on low latency or something like that, to sort of describe how coding fits. Yeah. So thank you for your time.
Okay, thank you. Comments? Questions? I think we all agree with the conclusion. It's not a big surprise for us, but as you mentioned, it's maybe something that should be more communicated well. We should find a way to better make people aware of these fundamental limits, and one way to reduce up to a certain point this latency in semi-reliable or reliable communications. Yeah. The two documents that you mentioned at the end, the two internet drafts, one of them is the one from Yariarko is now timed out, expired. Not the other one. Did you try to contact them?
Yes, I talked with Linda. Yeah, and she was very open to adding stuff there to the document. So okay. I think that's something that we would do.
Yeah, sure. That's a good.
Yeah, we did that. Yeah. But I don't know if it's something that this group should also have a document on low latency and coding, or like.
You mean our group? Yeah, sure.
Okay.
Yeah. It's implicit, but making it explicit perhaps is also something important.
Yeah.
Yeah. Thank you.
Okay.
Thank you, Martin. There is one presentation left for myself. Yeah. Okay, so it's a quick presentation about some related work we have done, and that is almost finished in the TSV working group, where we specifically explained that using coding, and in particular sliding window coding, could help in reducing latency. So it's part of this big communication on, FEC can help reducing latency, but it is in this TSV working group. And more specifically, what I would like to talk now today afternoon is about this, what lessons we've learned on by specifying this RLC FEC scheme, and more specifically on the PRNG aspects. So there are a few important things that we should be aware of. It could help. So this specification has been, I would say, a little bit difficult and long at the end, for two reasons, basically. First of all, we totally overlooked the problem associated with the PRNG. That's a mistake that we've made. And we fixed that only, 1 year ago, around May 2018. We thought we were close to the end, but in fact, we totally overlooked this PRNG stuff. The Park-Miller linear congruential PRNG that we have been classically used for years is totally broken when it comes to generating coding coefficients. That's something we need to be aware of. It's broken because it will basically produce for certain types of seeds the same first few parameters because of the way it works. I mentioned this and explained this more in details in Montreal meeting. So unless there are questions on this, I wouldn't like to come back on it, but keep in mind that it's broken. So we had to find something else, and we found this great, another great PRNG, much more modern and more mathematically speaking correct, that produces better pseudo-random numbers. But this second specification is based on source code, on C source code. So the specification is the implementation, or would say the implementation is the specification. There is no pseudocode specification of it. And it created several side problems that we found very difficult to solve. So this is what I would like to explain. So basically, the main problem is about copyright and license. It may seem something quite easy, especially when the source code is provided with a BSD style license. In fact, BSD style license is the one that IETF is using. But still there is a slight difference, and the licensing aspect also, the copyright aspect, the copyright aspect is extremely hard to solve unless the authors of the source code are also authors of the internet draft. So that's the only way, the only clean way we found to solve this copyright and license problem. Having those C implementation authors also be internet draft authors. That's the clean way. Otherwise, you will never find a solution. We tried, we asked, Spencer and Miria asked the IETF legal department, we tried to find another way to address this problem, but it was almost impossible. So that was the first problems when we have this C source code reference implementation. Another problem is interoperability and determinism. I will come back on this. Sometimes it can be quite subtle. I was not aware that the C specification, C99, C11, those and C specification are a little bit unclear on how to, for instance, represent negative values. So most of the compilers, I would say 99% of the compilers and target environments you may want to use are using two complements for representing negative values, which is more or less the basic assumption you may have on this, but it remains that it's not specified, it's not mandated in the C specification. So you may find a situation where your compiler uses one complement representation or something else. And depending on this, depending on the way you implement your stuff, it may create deterministic problems. It may end in different results. So that's something we discovered. Fortunately, Benjamin Caduc was aware of this, and he mentioned this during the ISG review. So it was great. So that's the problem. So we end up with this TNMT42 PRNG, which is, from a mathematical point of view, quite good. It produces good quality pseudo-random numbers. As I said, it comes with a C reference implementation. We further specified 3 internal parameters. You may find millions of such triples. We selected this one to make it easy to use. But keep in mind that if you use a different triple, then you end up in a different pseudo-random number sequence. So that's possible. So we specified this. We also we have also been very careful in terms of determinism. For some use cases, determinism is not an issue. When you want to create simulations, well, it's not a big deal if what you get on your laptop and what you get on a different laptop are a little bit different. But when it comes to FEC schemes, then it's absolutely mandatory to have exactly the same pseudo-random sequence with the same seed. So this is what we've checked, and we produces this table with 50 PRNG, pseudo-random values that must be checked if you want your PRNG implementation to be validated on your target platform. So that we made many experiments on different types of platforms, 64 bits up to down to 8 bits target teeny boards using Mac OS or Linux or Riot, which is an operating system for IoT devices specifically. So that's something important. We clarify this. Another point, last bullet. This PRNG produces pseudo-random 32-bit numbers. So that's the goal of this internet draft and this PRNG. Now, in some situations, you need to scale down this 32-bit address of value space into something smaller. Like, for instance, with RLC, we need pseudo-randoms numbers between 0 and 15 or 0 and 255. So in that case, you need to specify how to do that, and we did it. But we did it in the FEC scheme specification and not in the TinyMT42 internet draft. So if you want to use this, and if you have such requirements, then you have to provide your own scaling down function. But that's not a big deal. And the good news is that, yeah.
Morten Petersen, why do you need that?
Sorry?
Why do you need that?
Because I need a pseudo-random number between 0 and 15 and 0 and 255 for the coefficient generator function.
But if you just generate the bits and you can just consider it a bit stream, right? And then you just use, however many bits.
Yes, you may do that. Yes, that's another way to do that. That's typically what I call this function that gets the 32-bit pseudo-random number and generates this, let's say, 4-bit or 8-bit pseudo-random number that you need for your specification. So you have to provide this function. That's one way to do that. We used a different way, but it's also valid. But you have to provide this in some way.
Yeah. And why the 50? Is that just
No, 50 is
okay.
It's considered as a good value. No, it was also the size provided by the authors themselves. So. And last slide. So the good news is that it's not yet finished, but almost. And we hope to have this RFC if we are optimistic for next IETF. We'll see that. But I think it's feasible. It has the source code has already been reviewed by ISG, and we cleared this licensing copyright. So it should be feasible to have it available for next IETF. Anyway, if you need a PRNG, this is clearly an option. You may find it's not appropriate for you, but in that case, you have to provide your own PRNG, and it can be, as I said, something a bit complex to achieve. Yes.
Did you benchmark the time it takes to seed the PRNG? Because that's something that we experienced has a huge. It's very, very different. And if you have a very high throughput application which basically uses the seed as the way of generating the coefficients, then you also need a fast way of seeding on the decoder, for example.
Yeah. Yeah. Yes, we did it. We didn't identify any problem. But I agree with you. It's something that should be considered. In fact, the way we use these PRNGs for random linear codes in general is quite different from the way you use PRNG for other use cases. In our case, we need to generate a high number of small PRNG sequences, rather than a single very long PRNG number sequence. So the seeding part is something which is important because it will incur some computing time that could be non-negligible. But in our case, with this TinyMT42, the way it's implemented, we didn't identify big issues. Yeah.
It's going to be mandatory to use that one. I mean, in the if you have, let's say, is it up to the implementation or to choose or is this recommended maybe or will every implementation have to implement this specific?
No, it's not mandatory unless you want to use this ILC FEC scheme. So the ILC FEC scheme mandates that this one be used, but with the function we provide to go from this 32 to down to 4 or 8 bits value range. So this is mandated in that case, but if you want to use a different PIG, as I said, you are free to do that, but you will have to specify this PNG by yourself. And depending on the way it's specified, it can be a bit tricky, a bit long, depends.
Maybe I can add that I was there when the transport area people were asking questions about this, and they were extremely, I would say, strict in making sure that what was mentioned as a PRG was a true PRG. They were concerned, if I remember, I don't remember who was sitting at the table, but there was actually quite a discussion on that. So I think I actually think the work that was done there is very, very interesting, since we've been talking about random coefficient in this group for quite a long time.
Yes, random coefficient is not that easy to achieve.
Random coefficients are not random, essentially.
Yeah. We need to pay attention to that. Okay, so that's all I wanted to say. Thank you.
Thank you. Because since you're the author of this, I'll be doing the chair thing. Any questions about any other questions about the presentation, or not? Okay. Thank you. Thank you.
Welcome. So
I think we're done.
Yes, we're done. So I wish you all a pleasant period till next IETF and interesting work. So as we said already, we will meet in Montreal, and we will have this, yes, your own town, and we will also have this hackathon project. So do not hesitate. If you are interested, you can participate either physically or remotely. Both are possible. I think there will be fewer people there compared to this hackathon, but from what echo I already get. But anyway, we will find a way to make progress on this interesting project. So thank you, everybody.
Thank you. Alors, Poulette, elle a 28 minutes pour faire son vote. Tu penses qu'elle va le faire?
Blue sheets.
If anybody has, yeah, everybody's signed.
Okay for you? Yes. Thank you.
And I would like to thank David Oren for having taken the notes.
Yes.